In this video we're going to take a look at Nightmare, which is an easy Pwn challenge, and the description says, you seem to be stuck in an endless nightmare, can you find a way out? So we'll begin by downloading the file, copy it over to our local directory. Note that this is the last easy challenge in the Pwn category, so if you haven't watched the videos before this, I recommend going back through them. I didn't necessarily get the order right in terms of difficulty because at the time I didn't realize when I did the previous videos that there was this intro to binary exploitation series which has probably ordered these more accurately in terms of difficulty. I asked in Discord what people thought were the easiest challenges to try and make the way through, because it can be hard to determine based on the difficulty rating and the number of solves, because you don't know whether people who have rated the new challenges as easy only find it easy because they've done all the old challenges, which is quite often the case. So yeah, my order is quite different to these, but it is the order that I solved them in, so obviously I've been learning as I go, so I would recommend following the order that I put the videos up in anyway. But with that out of the way, let's go and do our basic file checks. So as usual, we begin by checking the file type. We'll see it's a 64-bit LSB Pi executable. It's dynamically linked, so it's not going to have all the functions within it. It's going to refer to external libraries like Lib-C to get any functions that it needs. And it's stripped, so we've seen this before. This means that we're not going to be able, it's not going to have debugging symbols. So this is done to improve performance, but it also makes the reverse engineering and static analysis more difficult. But that's fine. Let's do our check sec. So we can see this time we actually have most of the protections enabled on the binary, and we'll go through these in reverse order. So Pi enabled, this means that every time the binary loads it's going to be at a different address in memory. So if we want to write an exploit and code in the address of different functions or variables or ROP gadgets or whatever, we're going to need to leak the address to find out where the binary actually begins before we can access those different offsets. NX enabled means that if we are able to overflow the buffer and inject some code onto the stack, it's not actually going to be executable. It'll be marked essentially as data rather than as code. So in the challenges we've seen previously, this would indicate then that the chances are we would have to use some kind of ROPs to get to Lib-C, return to Lib-C and maybe call system. But we'll see actually in this case as well, we also have stack canaries. So if stack canaries are in place, it's unlikely there's going to be a buffer overflow. If there is, the goal of the buffer overflow will need to try and leak the stack canary and then overwrite it with the correct value. But considering this is an easy challenge, that's probably not the case. So it doesn't look like we're looking at buffer overflow. We're certainly not going to be able to execute code in a stack, and we know we're going to have to leak this Pi base address. One thing we need to look at is this RELRO. So in the previous challenges we've looked at, we've had partial or full RELRO. This is the first that we've had no RELRO on. So for this, I'll refer to an article which I found. I'll put this in the description as well. And this talks a little bit about the RELRO protection. And to describe this, they talk about a exploit. So we know from previous challenges that the global offset table will, whenever a function, say from Lib-C is called, for example, let's say puts. Whenever puts is called, the address of the function in Lib-C will be written into the global offset table after it's been called, because it'll have to make that call out. It'll write that so that in future it knows, okay, this is the address. This basically describes an exploit whereby if that occurred and we then had write access to the global offset table, we could overwrite the address that puts is linked to, so that next time it goes to call puts and thinks, okay, this was the address that we got puts from in Lib-C, actually we've replaced it with another function, maybe system, so that we can get a shell. So they describe this exploit, and then say the way you can get around that is using RELRO. So normally we see the partial or full RELRO, meaning that the global offset table will be read-only. So they describe this protection a bit more. I'll not go through this whole article anyway. I'll let you do that in your free time. But that's just something worth bearing in mind, because this kind of gives us a hint as to what's going to be, what we can expect to see in the challenge. We know now what it's not going to be. It's not going to be us injecting code onto the stack to try and get it to execute. It's unlikely to be a buffer overflow at all. We know we're going to have to leak the base address, and then we also know that the global offset table is going to be writable. So it gives us a good idea before we've even looked at the program what the challenge is going to entail. We'll also check the strings -n10 nightmare, and we can get an idea just from the text that we see here. We're going to have a couple of different options. We can scream into a void, we can try to escape the nightmare, and then it's going to take some input off us, and we're either going to be able to escape the nightmare or we're going to be told it's impossible to exit. So not too much here, because it's been stripped. It's not too much for us to look at. So let's make this executable as well and just test out the functionality. So we run the program, we get this menu as we expected, and we're told we can scream into the void, we can try to escape this nightmare, or we can exit. Let's scream into the void. We get the hit me up. We can put in a long message, although we're not expecting to see a buffer overflow here anyway, so because of the stack canary. So there's not really much point. Let's try to escape the nightmare. We get asked to enter an escape code, so we'll say 1, 2, 3, wrong code, what do you want to do? We can try that again, and we get an alarm clock. Okay. Let's just run it again quickly. And we can try to escape the nightmare. Let's try and exit. Seriously, we told you it's impossible to exit. Okay, let's go back to the escape code. Let's try and put in a longer value, and you can see that it prints it back to us, but there's no overflow there after it got to too many characters. It just moved on and sent that in to the scream into the void in the main menu. We could, I think if we try ltrace, we're not going to get much. Yeah, we get nothing because the debugging symbols have been stripped. So we'll want to go and take a look at this in Ghidra. We'll decompile the code and see what's going on behind the scenes. Let's create a new project. We'll create a new project. And import the file. Just do all the default OK and yes. I wish it was a little bit quicker to open Ghidra. I wish you could just type Ghidra in the name of the binary and you were just in the disassembled code. It's such a slow process. Okay. Like just all these, just do all the defaults. Maybe there is a way. If somebody knows of a way, let me know. Okay, and we get into Ghidra. We have our assembly code here. We have the decompiler here. We have our sections up here. So, for example, we can go and have a look at our global offset table. If we double click that, we can go and have a look at the actual addresses that are here. So, for example, as I was mentioning earlier, if we have calls, I think we use the example puts. So puts in this example is going to be in the global offset table. It's going to point to the actual address of puts in Lib-C once that's been called. So yep, that's worth bearing in mind. We can go and check out our sections there. We can go and have a look for strings if we wanted to just quickly try and find a specific function, or we can just go and have a look at our functions here, which I'm going to do. And notice that we don't have our main function because it's stripped. So we go to our entry function. We can see the function here. Then we'll go straight to the first function that's called, and this is clearly our menu. So we have, there's our function with the alarm that goes off, setting up that alarm to go off. We have a couple of variables declared here. This is going to take the input off of us, so you can see we have a function. It's just putting out the menu, and then it's looping, waiting for us to provide an input. If we provide 3, it's going to say, sorry, we told you it's impossible to exit. If we do greater than 4, it's just going to say no can do. I don't think we actually tried that actually. So if I try 4, it's going to say no can do, 5, no can do, etc. And the main functionality comes then whenever we enter a 1 or a 2. So if we enter a 1, It's going to scream into the void. And here we have the buffer is defined at the beginning. We have 280 characters, and then it reads in 256 characters from us. So we can go and have a look at that there. It's 100 in hex, which is 256 in decimal. So there's no overflow. There's nothing we can do to overflow the buffer, and even if we did, we have the stack canary. So notice this stack check fail. So at the beginning of the function, you have this local 10 variable, this long 10, and it's assigned a value here. So the value this is assigned to on runtime is going to be placed on the stack. It's going to run through the function, and then if we did somehow manage to, if there was a buffer overflow vulnerability, and we would have to overwrite that stack canary, and then whenever it gets down to the stack check fail, it just say stack smashing detected or something like that, and exit the application. So in some cases, you might be able to leak the actual canary and then overwrite. Whenever you actually write your shellcode or write your ROP gadgets, ROP chains, whatever, you might be able to overwrite the stack canary with the correct value as well. Sometimes these are just implemented in CTF challenges. You'll see stack canaries that are just kind of implemented manually, you know. So it's they're a bit easier to brute force and things like that as well. But yeah, it doesn't look like that's going to be the challenge here. So it takes this input off us, it prints it back with printf. Okay, so let's go back and have a look at the second menu option. So we have a buffer this time of 6 bytes, 6 chars, and we have our stack overflow, our canary is set up again as well, stack protection. It asks us to enter the escape code, and then it's using fgets to read in 6 bytes into this variable local 16. And then it calls this function, which is doing string comparison with the input and lulz-k, and it returns, if that's true, it's going to return and say congrats, you've escaped this nightmare, and then exit 0. So we can go and do that, but obviously that's just going to exit the application. It's not going to give us a flag or a shell. So we'll try and do it. Escape this nightmare, we say lulz-k, and we get congrats, you've escaped this nightmare. But obviously that's not what we want to do. But if we don't supply the right value, it's going to go down to printf, and it's going to print out local 16 back to us. So hopefully you've watched the videos leading up to this, and you'll know from leak test, I don't know, maybe we might have done it in one other. We were able to exploit a format specifier vulnerability with printf, whereby because they haven't specified here that they want to print what we input as a string, they leave us with that ability. So we can say, actually, can you represent this as a pointer? Can you represent this as a decimal, a hexadecimal, or even we can use it to write to memory as well. So because this is printing back to us, we'll actually be able to leak values. So let's go and test that out. Before I demonstrate this, let me bring up an article alongside it, and let's just have a quick look as well at the format string specifiers. So we can go and get a list of the different specifiers that can be used. Let's go format specifiers in C, and this will give us a list of all the different types of data types that we can use to represent data as. But this article as well, in the leak test, I kind of went through this step by step, and I think it lays out the vulnerability really well and how to exploit it. So if we go through this just a little bit again, we can see here we can print out values as hex. Let's go and do that while we have it open. So we'll run nightmare, and let's try to escape this nightmare, and then we're going to do X, and you'll see there it's printed out in hex. We could try to print a pointer as well. Oh, we need to go back into the nightmare. Try to print as a pointer. We actually get no can do now after running that, which is interesting. Let's try and run that again. Scream into nightmare, and there we were able to get the pointer. Let's try and go escape code, and let's try it as a string, and we got lulz-k. So actually we know that the first element on the stack that we're trying to print there is actually this string, or it's not this string. You can see here, if you can, I don't know, hopefully you can see past through my terminal there. Let me minimize this. So the %s indicates that data is a pointer to a string. So actually this looked at the memory address. It was a pointer to a memory address, and it's printing out the string that's being pointed to. So if there was actually a string on the stack and we tried to print it as a string, that wouldn't actually print the string. It would try to interpret that string as a memory address and then try to print whatever's at that memory address, which quite often isn't a string, which means if you try to, we were lucky in that case, but if we tried to, let's try this again. I'll do %s, and you see we got a segmentation fault, because basically the second thing on the stack, whenever it tried to look up the string at that memory address, it said whatever's on the stack is not a memory address, I'm not able to do that, and crashed out. So that's worth remembering, because in some cases there might be a flag just on the stack for you in a string, and if you try to print it as you might think logically using the %s, actually you won't be printing that string, you'll be printing whatever that string is pointing to. And in that case, it's probably not a string, so it's so in that case, what you would do is you print it in some other value. You can print it as hex, you can print it as decimal, whatever. You can print it as a different memory data type, and then just go and convert it to strings elsewhere. And you can just add that into your script to do that as well. So we can see then in the example in the article as well, they tried to print out the 20 items off the stack. Now if we try to take even a copy of a few of these and run this again, let me scream into the nightmare, we enter this as the escape code, and you'll see that it printed out some values there, and then it's looped through the menu, because if we go back to our code, it was actually only 6 bytes that could be entered here. So that's going to be an issue, and the issue that we would use to get around that is the percentage and then the decimal dollar and then the data type. So we can say we actually want to print just the 10th element on the stack, and we want to print it as hex in this case, and that means we can just write a script to fuzz the program and to loop through and say print the first element, print the second element, print the third element, etc. without risking overflowing the buffer, or without if we don't have enough room. Okay, so I think that'll do for now. We can look at, we'll refer back to this later. So we're going to create a fuzzing script now. Let me copy over the script that we had from leak test, fuzz.py, and we'll open this up, go and make the changes we need to. Shouldn't need to change too much here. Obviously change the file name to nightmare, and the syntax is going to be a little bit different here, but essentially we're looping through, we can loop through however many values, 100 values, and we're going to print out each of those values off the stack. So our aim here is, we know that I've not talked exactly about what the exploit is going to be yet. We'll leave that until later. Whenever I approached this problem, I didn't even look into what the exploit was going to be at all until I had first leaked some addresses. So I knew that the fact that we have the format string vulnerability there, and that we know that pi is enabled, we know that there has to be some way for us to leak the address of the base address of the binary, and if there's no buffer overflow, etc., then it obviously has to be leaked off the stack. And this is quite similar to leak test. So we leaked, I don't think pi was enabled on that, but we leaked a stack address and then calculated the offset to Lib-C and got our functions and things. Anyway, let's update this. So it's not gonna say hello. What do we get? Let's run the program again. Nightmare. It's gonna ask, what do you want to do? And after we get this angular bracket, we want to say 2, and then we're gonna get another angular bracket, and then we're gonna give it, say, a pointer. Well, let's give it the actual syntax we'll be using. So we'll be using something like, let's say we want to print the 10th element, and 10th element, and then we'll say $p, and then it gives us our address, and it comes back with this, and then again we're gonna send the same thing after the OK. Alright, let's go and test it out. So we'll say here, before we send that off, we need to do send line after, and whenever we see this angular bracket we want to send it a 2, and then after we get the next angular bracket we're going to send it the payload. So we'll say again send line after, and it's just going to, the format specifier I just gave is just going to do that, and this is going to be a way for us to get over the fact that we don't have much space there as well. So let's check that out. Python fuzz. Alright, so we've printed out some values. Although it looks like we're missing some, and we're getting this no can do as well. If we have a look at what we're actually getting here, notice that with the first addresses we're also getting this angular bracket and a space there before we actually get the address. So let's modify this slightly. Before we take the result, we'll say we'll do p.receive until, and then we'll get that angular bracket and the space. Let's test that out. Alright, so that's looking a little bit better, but we're still getting some problems. Let's go back here and we'll change this to a pointer to print out some addresses here. We want to see what we can leak. So looking at these addresses, it looks like we might be able to calculate the offset to the pi base. So the base, we know that it's going to load, the application is going to load at a different place each time in memory. If we can calculate the offset to the pi base from here, we can use that offset every time the program runs to calculate the base, and from there then we can find other functions. We also might want to get Lib-C as well, so there are addresses here which look like we might be able to find the offsets to Lib-C. You can tell with the 7FFF addresses. But notice that we're getting up to 10 and then we're starting to have issues here where it's printing out, it's not printing out the actual addresses. So let's explore that a little further. Let me run nightmare and we'll try to escape. We'll input the percentage, let's do $9p, and you'll see here it's printed the address out. Let's try and do that again and do percentage $10p, and notice that it's printed out a stack. You can see there it looks like we've got our binary address and a stack address. Now if we try to go back in, we get no can do. It actually won't let us back into the menu. And notice that whenever it printed out this address, it printed out a space below it, and this one didn't. So the difference seems to be the number of characters. So here we have 4 characters, here we have 5 characters. So even though we've managed to shorten this down so much, rather than having to print out 10 times percentage p, we are still having problems. And that's because if we go and have a look at our actual code, we know that it's reading in 6 bytes. We need to allow for the null terminator, otherwise we're going to have issues there. So okay, so we'll come back to this later anyway, but let's move on for now. I'll just note that if we were trying to print these as strings, that if we try to run it we will get only 2 strings will show up. But if we were to modify this, I'm going to modify this and we'll say we'll launch a new process on each occurrence, and then we'll close the process each time, p.close. And then if we run that, we haven't got 10 values because it's run through all 10, but any time that it's come into any that have run into a segmentation fault, it's just not printed it, and then it started the program again for the next occurrence. So for example, in that first case right here where it crashed out at the second one, here it just hasn't printed it, and the reason it crashed out was because the second one was 0x6c, which if we go to ASCII-to-hex.com and put in 6c, we'll see that was the letter L. So it's tried to access the letter L as a memory address and print the string that's that's held there. And obviously it's not a valid memory address, so that's why it's crashed. So that can be a way, if you do want to try and print out strings in that fashion anyway, and you want to get over the segmentation fault, you basically just need to launch a process each time, or launch a process and each time it crashes then just launch it again, which is probably a better way to do it. We're going to begin to go and put together our exploit script. Let me grab a template, as we usually do. We'll get the pwntools template, just copy it here to exploit.py for now, and open that up. A couple of things we'll do here off the bat. We'll go and put in the correct binary name. I'm going to change the context log level to debug. So I'll go through this every video. You're probably bored of hearing it now, but the context binary is set here. So everything we do in this script is going to use the architecture and the bits and the operating system that's defined in the binary we load, which is this nightmare binary. We're setting the context log level to debug, so we can see everything behind the scenes that's sent back and forth, which can be great for reverse engineering exploits. So you might, if you watch the leak test video, you'll know that I kind of struggled with putting together the manual exploit in that case, and the way I got around that was using the format string function or library in pwntools and automating the process, and then using this debug method log level to actually see what the exploit was being sent behind the scenes, and essentially reverse engineering it that way. We have a function here to find the offset of the instruction pointer if there's a buffer overflow. We don't have a buffer overflow here, so I'm just going to remove it, and we'll remove this as well. We're not going to be writing the payload to a file, so I'll take that out, and in fact I'll just take all of this out. One thing we'll probably want to do is just IO interactive at the end, because we're going to be trying to get a shell here, but let's yeah, I'll take all of this out. Oh, let me also just mention as well, because this context binary is set, what you'll often see is if you were trying to get some shell code, for example, you wanted to generate a shell with shellcraft or do shellcraft, you might do something like shellcraft.linux.x64, or it might be x64.linux, I'm not too sure, because I use it so rarely now. .sh, or you might say .cat and then put in flag.txt. Well, because this architecture is set up here, we never need to worry about this part. All we'll ever have to do is say shellcraft dot, and that means we can basically port our scripts between different architectures and different operating systems a lot more easily, which is why this template is so handy. Also, if we were dealing with addresses and things, rather than saying p32 and then our address, or p64 and our address, we can simply just say pack and then put our address in here, or we can use that payload, the flat, as well. So we had this flat function. It'll normally give you a nice summary here, but essentially, yeah, it flattens the arguments into a string. So this function takes an arbitrary number of arbitrarily nested lists, tuples, and dictionaries. It'll then find every string and number inside of those and flatten them out. Strings are inserted directly while numbers are packed. So that'll basically do all of that for us if we're using this around our payload, which is normally what you'll see me doing. We also want to set up our GDB script as well. So because we're going to be trying to leak the Pi base address, or leak an address to calculate the Pi base address, should I say, and the Lib-C offset, we're going to want to find out what the Pi base is. So anytime we attach GDB, the first thing we want it to run is Pi base after it's initialized the plugin. And we can use break RVA as well to say we want to break at whatever offset of the Pi base. So if we go and find some code inside of Ghidra or disassembled from elsewhere, for example, our printf here is being called at this address 1438. So we can just say break at RVA 0x1438, and it'll set a breakpoint so that we can then go and have a look and see what's actually happening whenever that instruction is called. So we want to go and try and find out what addresses are being leaked and what the offsets would be from there to what we want to get to, which we've not even really discussed too much yet. Let's just worry about getting these offsets calculated first of all. I'm going to go and copy our fuzzing script, this loop right here. At the moment there's a breakpoint that's going to be set on every loop. It's going to set a breakpoint at the printf call, which was right here. So that might actually get kind of annoying. We're probably going to want to turn it off and then just try to have a look at the end. Let's run through this, and so we run through it. We see that we're getting our address back at the end each time where we're printing out that result. Let's actually go and strip that as well. It's not going to matter too much here, but just whenever see, we've got rid of the new lines at the end. Just whenever we're later on actually converting these into addresses, we're going to need to make sure we're not getting the new lines in there as well. Alright, we could change this to info if we wanted to reduce the amount of noise in this case, because what we want to do is we want to go and actually see what these are pointing to whenever we run the binary. So we could run this with GDB. If I just add GDB to the end, it's going to launch, and the first thing it's going to do is it's going to run pybase, which is going to tell us what the base is, and it's going to set a breakpoint at pybase plus the offset of this printf function when we set that breakpoint. So you'll see there it set that breakpoint, and that breakpoint is basically just the pybase plus the offset of that printf function, and it stopped at the breakpoint. Let's see, we can continue, and we can continue and just skip through each of those instances, and if we want to then have a look at what this address actually pointed to, that first address for example, let's do x and then paste that in. We'll see it's come back. Let's try and do x over s, because we actually know that that's the lulz string. And we could go through and basically do this with each element. So I'm going to run through a few different ones. We were quite interested, I believe, in... Oh, we've closed the connection. Okay, I'm going to try and run that to... Let me run that one extra... If we run it too many times, we're going to run into the issue with the size, but let's run this again, continue. So we were kind of interested in 8 and 9, so let's have a look at 9 first of all, because we're trying to find the pybase. So x over s. Alright, so you can print this in different formats. You could do x over 50x if you wanted to see more of what's printed there. What we're interested in is where is this compared to the pybase. So we have pybase. This gives us the pybase, and then we have our address as well, which is right here. So we could simply take these and subtract them. Let me do Python 2-c print, and then probably should have done that the other way round. Okay, it's not letting me copy that for some reason. Alright. Oh, I've copied the same address. It won't let me copy the second address for some reason. Okay, I can copy it from here. So we can print a value, we get minus 5333 here. So presumably if we go here and say x, or if we say, let's do pybase and help, and you can see that we can provide actually an offset. So we could say here pybase, and what was it, 5333? Yep. And that will give us this address, and then let's see, does that address match up with what we have? And it does. So we now know that the offset is 53333, which we can then go and add in to our script to calculate the pybase, and then from there we can always just go and put in offsets to different functions or different ROP gadgets and things like that that we might need. Okay, so let's close that down for now. let's go and add this to our code. So I'm going to take this script out. I'll paste this code in. Oops. And it was the 9th element. We're receiving a line back. Instead, we'll say here leaked address is equal to, and we'll convert it to int base 16. Then afterwards, we'll try and print this out. So we'll do info leaked address is equal to %#x, and then give it the address. Okay, I'll take this code out of here. We'll just do the same thing to try and get the Lib-C address afterwards. So we leak this address, and then we want to say that the pi base is actually equal to leaked address minus 5333. And then we'll print that as well, and just go and verify it in GDB, make sure everything's looking okay. I'll go to io.interactive at the end just to try and stop it from crashing out. And let's try and run that again. So we get our breakpoint here, we can see our pi base up there. Let's do continue. We've got wrong code, but you can see it stayed open. What we're interested in here is our pi base. So you can see pi base ends with 5000. And we can see up here that our pi base is also 5000, which means if we now say, for example, if we wanted to get to this printf function, it should just be a case of using that offset to calculate that. So let's go and try and get our Lib-C address as well. So let's run through the fuzz. Again, whenever we run through the fuzz, it looks like, let's try out our 8th address here and see what's there. So I'm just going to copy and paste this code, and we'll try and get the 8th. Grabbing the leaked address again, and then here we're going to update this for Lib-C, but for now we'll just try and print this out and see what happens. So this launches, it will grab our pi base. It's so hard getting the windows to snap properly on this. It'll get our pi base, it'll stop at our first breakpoint, so we want to continue. You can see there it's got that for us. Continue again, and now it's printed out this stack address. So we can go and Control and C here, so we get control of the window again. We can do X and then paste that in. We could try and run X over S to print it as a string. But we're not seeing any references to Lib-C there. If we were to try and type p system, we can actually print out the location of Lib-C system, and we could calculate the offset here. So we could say print out system minus and then the address that we're leaking, and grab that offset. But let's try this and see what happens. If we go and I'll uncomment this code, we'll set this to Lib-C base and system. We'll say this is system, and system is equal to the address that it's leaking minus, what was that number? So it might be minus this, it might be plus, I'm not too sure. We can try both and see what happens with it anyway. And then we want to try and print that out, and then we can go through and just confirm and see, does it point back to the same thing each time that we run it. If I run this again, and we want to continue again, Control and C, and we've got a leaked address, we've got system. So first of all, let's have a look. P system, is that the same? No. And if we check our system, if we try and print out p system minus the leaked address, we'll see that it's got a different value this time. So long story short, we could I'm not going to change that to plus because I know that's going to be a different value each time. If we go back and run our fuzz again, we didn't have many addresses to try, and I'm not going to try this address just to let you know that none of these actually will work for us. They're not going to give us an address that's going to have the same offset each time to Lib-C, so we do need to go for a higher value. So you might remember from earlier the issue that if we go back and we say update this to 100 and run through that again, fuzz, Python fuzz, the issue was that once we get past 10, it causes some problems with the formatting. So although we are still leaking addresses, for example, this 14 looks like it might be interesting. We have 30 as well, also looks interesting. The issue was that if we actually, let's run the program again and remind ourselves, if we try to escape and we say, alright, let's say that we did want to get this element 30, so we would say here percentage $30p, and then whenever we try to get into our menus after that, we're just going to keep running into no can do, and everything we enter, we're not able to get out of it. So I got stuck here for a while, and I'll go through this and show you the mistake that I made first, and how although it did work for me, I was only able to get this working locally, so eventually we'll have to change our strategy. But let's go through it as I did when I was solving it and see what mistakes I made, and hopefully try to learn from them. So at this point I returned to Ghidra and had a look at the code again, and we haven't really looked at the first function too much. Let's go back here. So we hadn't really looked too much at the shout into a void function, but essentially this has the same issue. We have this fprintf, and it actually reflects our input. So we have 280 characters, we're able to input 256, which means, and I didn't test this literally until I ran into this problem, which means if we try and run this nightmare and scream into the void, and then in this case let's try and even just copy and paste some pointer values, and if we paste all of these in, because we have enough room, we'll be able to just keep printing all of these pointer values, which is great. It means that we're going to have no problems in it's not breaking the menu. We're now able to say, okay, percentage $30p, and that's going to give us the address, and then we're still going to be able to enter in our escape codes and things like that. So I noticed this, and I basically decided, right, okay, from now on we'll proceed with this method, and we'll just use the first menu option instead. So let's actually go to our fuzz script first of all and just change this to 1, and I'll try and run through that again. Python fuzz, and you'll see we print out all of our addresses, no problems. It doesn't run into any issues where it starts printing out extra input. So we can see that things will be laid out slightly differently here as well. If we go back to our exploit script, we were originally using the 8th element, which was the 5.5 address, whereas now that's nil, so we won't be able to use the same element, but we can use the 7th, and we can pick another address to calculate the offset to Lib-C. In this case I actually used 38, so I think that was just what I had from the script, from the leak test script, I'm not too sure. But let's change that slightly then. Let's say in our exploit we're going to look at the was it the 7th address? Oh, instead of the 9th, that was, okay. So we'll take the 7th, and actually we'll just try and take the 11th here. So we'll take 7 as our pi base, and we're going to send 1 instead of 2. Again, we'll send 1 here, and we'll take 11. And then we're obviously going to need to calculate our offsets again, so let's just run through that. So Python exploit gdb, and okay, it didn't stop at our breakpoints in this case, notice, because our breakpoint was set at the printf in the other function. So we might want to go and change this as well. The fprintf, we set it at 138c. Let me go and do that. So we can put in here 138c, and that will change that breakpoint in future. But let's see if we can actually still, are we able to just take a look at the leaked address we'll have a look at our leaked address and see what the offset is from the pi base. Okay, so yeah, let's do this again while we're able to actually use the breakpoint. So this time the breakpoint will stop and we can continue. We get our leaked address and our pi base, so we want to say print out the leaked address minus the, I wonder, can we just enter pi base here? No, okay, so we actually need to copy and paste the pi base. Sorry, the pi base that's calculated here, not the one that we'd calculated incorrectly with the offset as well. Alright, we'll see it's 4480. So we can go back here and just modify our script and say 4480. That's our pi base. Let's see if we manage to continue this, and we get our leaked address here as well. Let's see what this points to. We needed to do it a bit quicker. X. Okay, it's not pointing to Lib-C by the looks of it. Let's actually, I'll go back and I'll use the one that I used whenever I originally solved this locally. So we've calculated our pi base, so we'll test that now, and we'll also just change this to 38, which is what I used originally, although plenty of other ones will do. Let's run that again. So we stop at our first breakpoint, we calculate our pi base, and we can go and have a look here, see if the pi base is the same. It is, so we've got that correct. We can move on, and we now get our leaked address here, so Control and C, so we have control of that again, and then we'll see what's at that location. And we're able to see then we have this GI IU default UFlow, and we can calculate the offset here. So let's say X system, and we have system, we'll do print the leaked address minus the system address. We get 236722. So we'll go back to our script and say, we'll just add that in, and that should give us the system address. Let's go, and it might need to be a plus rather than a minus. Let's test it out. So we continue again. We've got a system address here, so I'll just take a copy of that and do X, and there we've got Lib-C system. So we know that then each time we run this, it's going to correctly calculate the offset to system. So now we can go and calculate other things from here. So if we do here LDD and nightmare, we see our Lib-C library here. So we do readelf-s, and we'll grep for system, because that's the address we're finding. We'll see that this is the offset from the base of Lib-C to that function in whatever version of Lib-C that I'm using anyway. Yours is likely to be different. So here we would say then our Lib-C base is equal to system minus, and then the offset, which in this case is in hex. We've been doing these in decimal, but you can do these in hex as well. And then we can print out our Lib-C base address. This means as well any other functions that you need, you can do the same thing for. If there are strings as well, we can also do that. Strings dash, what do we need to do? A dash t dash x, and then give it the Lib-C grep bin/sh, and we can find the offset of that as well. So if it was needed, we could say bin sh is equal to Lib-C base plus, and the offset to the bin sh string. We can print that out as well. And then we can just go through and just test this all out, make sure it's all working properly. It's going to stop at our breakpoint, continue through both, and we can just have a look at each of these addresses. So we've got this bin sh address, so let's do x bin, and you can see it's printed in hex here, so we can do x over s to print as a string. we get bin sh, so that's good. We could do x system, and we'll see that Lib-C system is our AE50, which is what we have there. So we can just go through and make sure everything's adding up. But it looks like we've calculated all our addresses and offsets properly, so let's move on to the next part of this exploit. So if we remind ourselves what we did next on leak test, then it was looking at this %n format specifier. So it's a special case format specifier. Instead of being replaced by a function argument, %n will cause the number of characters written so far to be stored into the corresponding function argument. For example, the following code will store the integer 5 into the variable numchar. And then we have this example, so there's 5 ones, and that's going to be stored at the address into the variable numchar. So if in the previous example that we were looking at, I think we had a comparison between some values, and we wanted to overwrite 2 of those values with 0 to make sure that the result always equaled 0. So in this case, we're going to use the write functionality for something different, but the principle is going to be the same in terms of writing data to different addresses. So before we jump into the main part of this exploit, let's just set up the format string specifier. We want to find the offset in pwntools, so I'm going to look for the format string documentation, pwntools. Let's open this up, and we have some examples here. So let's go. So here's an example here, and yeah, so this is quite a close example to what we worked on in the previous challenge in leak test, whereby we created this format string object and we set it to execute this function. It'll find the offset that it needs to write data, and then we can just pass in write arguments. We can say we want to write leapbabe at this address, and we want to write 0 at the leapbabe address, and then execute writes. We'll automate all that for us, and then we can just go and debug it if we want to see exactly how it actually structured the payload. The last payload wasn't as complicated as this one's going to be, so I'll not be attempting to do this one manually first. I'm just going to jump into using this format string. So let's take a copy of this, and we'll add this here where the program starts. We also need the send payload function as well. So let's grab this as an example. And we'll add this here. And this is basically going to do the menu stuff for us. So let me try and take a copy of some of this code. IO send line after it's going to send the 1. It's going to send, in this case, I'm going to change this to just payload. It takes in the payload. It's going to receive the same, and then we're going to return io.receiveLine.strip. And this means we can do something cool, in that not only will this be used to identify the write offset right here, but we can also use the send payload throughout the code then. So let me try and see the first example here. So a leaked address, let's take this format that we would have been sending. We're going to send this to send payload. So in here I'll say send payload. We'll send that as the payload to send, and that means we can just take out all of this because all of that's going to run anyway whenever the send payload occurs. So that's just going to grab the leaked address straight away for us, and we can do the same down here as well. So we'll grab the 38th element, and we should be able to just take all of this out. Let's just run that and make sure that's working okay first of all. We've got an invalid. Oh, I didn't do the send payload here. Send payload. Try that again. And that's looking good. So it runs through. You can see it's found the format offset as 5, and then it's leaked our address as fine. We can go and change this to debug if we want to see what it's actually doing in terms of finding that offset. So if we set that to debug, you can see that it's sending different lengths of strings, and it basically it's sending the cyclic pattern, and it's sending these until it's able to write some of the cyclic pattern to the string. So let me see, it's found the offset at 5. The reason it found the offset at 5 is every other time it sent this, it leaked an address off the stack. It was only once it got to 5 that what it leaked off the stack was actually what we had injected. So it knows now how to write to the stack, and it can use that then to do the format string exploits. So let's exit that. Something else I forgot to do actually, rather than creating a pi-based variable here, we can just update our elf address to equal this, and then use that instead of pi-based, because that'll mean that if we try to access any functions or ROP gadgets and things that we just search for in the binary, it'll know what the address is because we've updated it with the leaked address. We can do similar with Lib-C as well, which I'll probably do another bonus at the end of this video. But if I don't, I've done that in previous videos. The last video, you can go and take a look at an example of that. Now we're going to look at the main part of this exploit. So as we were talking about earlier on, the goal of this, I've closed down the article, but the goal of this was to overwrite the global offset table with a function, because we're not able to perform buffer overflow, we're not able to execute code on the stack. That's basically our only route to get a shell, will be to overwrite a function in the GOT. So let's look at how we can do that. I'll just mention first of all as well this format string, if anybody knows how to use this properly, because there are some things about it like format string dot leak stack. Like there's no documentation. If you search leak stack, if you search this function on the pwntools documentation, in fact let me go here. There's nothing mentioned here. If we go leak stack, nothing at all. And if you search for it as well, if you search for it here, leak stack, there just doesn't seem to be any mention of that specific function, so I'm not really too sure how to use it. I've had a look at the code, but yeah, I can't really work out, is it something which I could be using to make my life easier, or is it just a function that's used automatically by the format string object, which there's no real need for me to have access to. So if anybody knows how to use these format string exploits better in pwntools, let me know. Anyway, so the writes that we're going to want to perform, let's go back to Ghidra and take a look at the GOT section. So there are some different functions in here. Essentially, we're going to want to replace a function with system, and for us, there are some. I had a look at some different functions to do this with. I was trying to do this with puts originally, but if we go, let me try and go back here. If we go to our second function, where it asks us for the code, right here it calls printf afterwards, and printf, let me highlight it. You can see there printf takes a pointer to a string, so from the RDI. So essentially, if we can replace this call to printf with system and then pass in a string, in our case bin sh or just sh, then we should be able to get a shell. So if we go to our GOT table again, let's go back there, we have printf right here, and the reason I'm saying printf, if we're going to do the write, I'm kind of jumping backwards and forwards here, I'm sorry about that. We're going to do the write here at the first function. So if we do the write here, it's going to call fprintf. It's going to do the overwrite, and then we're going to go back to we're going to return to the main menu. Can I return there? No. Okay. It's going to return to the main menu. We have our menu which is printed out here, so it's going to put most of that. It's going to printf this, but it'll cause an error, but it'll still allow us to continue. And then we can hopefully go into the second function, and it'll ask us for the escape code again. It'll have some issues with that, but then but the errors won't cause it to crash out. And then whenever it goes down to printf here, that's where it's actually going to reflect our input, which is going to be the bin sh. So we need to combine both these functions essentially. I hope that makes sense. I might not have explained that too well, but it might make more sense whenever we go through it here. So printf, we can see that the offset is 3568. So let's go and add that to our code. We'll say our got printf is equal to, and we're giving it the elf.address plus 0x3568. We can print this out and just go and verify to make sure everything is looking alright. So if we run python exploit gdb continue, oh, we have to continue through these offset things now as well. Continue. Okay, and we've got our got address here, got printf, so let's do x, and you'll see here printf at the got.plt. So we know we've got our offsets right. So essentially we're gonna, let's go back to the, oh, I've closed down the pwntools documentation, but yeah, essentially here we can now say, we're going to want to say format string dot write, and you can see here it takes in an address and it takes in the data. So we want to write over the got printf, which we're able to do because there's no RELRO, and we want to overwrite it with the address of system, which we have right here. We then need to execute the writes, so we can do format string dot execute writes. And that should perform the write for us. So we're going to overwrite that, and then we need to go back through our menu as well. So we're going to want to go into the second part of the menu. Let's actually run through that and see how that looks. Python exploit. Okay, so you can see it's sent off the exploit here. That's a lot more complicated than the leak test exploit. I would have a hard time deciphering that manually or preparing that manually, to be honest. So we've got our got printf there, and this is okay. We're expecting to see some errors. Let's go back to our script. We're sending line 2. Let's do io.receive again. And then try and send off sh. So we're overwriting the got printf address with the address of system. We're going back to the main menu, hitting 2 because we want to go to this printf statement, because that's the only place that we're going to be able to reflect our input, and the input that we want to reflect is this sh. So if we run this again, you'll see that now we're able to list the files, and we would be able to print our flag in this case. So even though we get some errors, that's nothing to worry about. Let's run this again, gdb. Let me just continue through. It's finding the offsets, continue. It sends off the write exploit. I wonder, can we see this changing? So that's set to the got.plt. Oh, okay, it crashes out. I guess because the breakpoint is set maybe at the printf, which has been replaced by the system call, that might cause problems there. Okay. Well, we have it working locally anyway, so let's test it out against the server and see what happens. So we'll go ahead and spawn a server. Take a copy of this address, and we can just run this then, gdb remote. Not expecting this to work anyway, because the Lib-C version is going to be different, so the offsets to, or is likely to be different, so the offsets to the system functions and things like that are all going to be different there. But let's try and run it and see what happens. Oh, I shouldn't have run it with GDB, I meant to run it with remote. So run it with remote, and you'll see here we got list index out of range when trying to identify the offset. So this is where we'll see the huge mistake that I made whenever I was trying to solve this. So whenever I was trying to debug this, I figured, well, we'll just find the offset locally and then just run the exploit against the server. But it's not quite as simple as that. Let's see what the difference is between the local and the remote version of this. If we run this locally, do nightmare, scream into the void, and we're trying to retrieve, let's say we're trying to retrieve the 38th pointer. So we'll do percentage $38 $P, and that's our stack address that we're trying to leak. Great. And we can just close that out. Now if we try and do this remotely, let me do ncat at the address, scream into the void, and we send it that percentage $38 P, and we get nothing back. So the functionality is very different, and as the description says, you're essentially screaming into the void here. So on the server, whatever input you provide there is not going to be reflected back, which is an issue for us, because whenever we were trying to use the second option, let's go to the second option, if we put in percentage $38 P, in that case it's nil, but after that we get this no can do, we can't use anything, which is why I moved on to using the first option instead of the second option. But now that's basically out of order, we're not going to be able to use that. If we were trying to use the values between 1 and 10, we're not going to be able to find the offsets to Lib-C, and if we try it above 10, we run into that problem with the menu. So how did I solve this? Well, I basically had to work out how we can get back to the menu. So let me run this locally again. If we run it locally, and let's say we want to print percentage $38 P, it'll print it, but it gets back to the main menu, and then obviously 38's not right here because we didn't go to the first option, so all the stack values are different. But now we try to go 1, we try to go 2, we try to go 3, we can't do anything. But if we try to go 2, 2, it will actually say now enter the escape code 123, wrong code. So that actually fixes the menu. So it took me a while to work that out, but that essentially means that we can grab any address up to 100 from that second part of the menu, and then we just need to send in either 1 1 if we want to go back to the first menu, or 2 2 if we want to go to the second menu. Okay, so I realize this video is getting quite long, so I've just copied over basically an updated solution here. So now that we know that we can actually print out values which are above 10 in terms of the pointer values from that second menu list, I was able to update this, and I made a couple of changes. One thing you'll note is that the menu option here is now passed in as a parameter, and we use a global variable. That means that whenever the program starts, we can set that to 1, and whenever we're trying to find the offset of the right vulnerability, it'll use 1 here, because if it uses 2, it'll crash out and it won't find obviously the right offset because there's not enough space. But after it's found the right offset, we want to set the menu option to 2, because we're going to go through and we're going to leak the addresses. This is basically all the same as it was previously. I'll run through this in a second in the debug mode. So it's going to run through those, it's going to calculate all our addresses, and then it's going to set the menu option back to 1, because we then need to perform the write. But in order to perform the write, we also need to send 2 1s. So I've added in this extra 1 here, so it'll send 1, but then it's also going to, whenever we do the write, it's going to send this payload, which is also going to send 1, which is going to, as we saw in a previous example, let me just do this again, nightmare, we go try and escape, and if we enter 1 2 3 4 5, we're not able to get into 1, but if we do 1 1, now we're able to enter in our input. Okay, so that's the reason that that's there. Anyway, seems to be needed to get the menu working again. I've just put there. And then it's going to perform the writes, it's going to grab our shell, and this should work for us. But obviously the addresses are going to be different, so I've set this up to work locally. You'll note that I'm using some slightly different addresses here. So let's run through this in debug and see what's different. Exploit GDB. Going to continue, so it's leaked all of our addresses. So our leaked address here, I'm going to take a copy of this. Our leaked address, you can see, is libc start main plus 234. So all I've done here is set libc base to equal the leaked address minus 234, and that's what we use then to calculate the offset to system. And this means that whenever we're doing this online, let's actually go and test this out now against the remote server. Do we still have the remote here? Test against a remote server. We're not able to list anything out because we've got our end of file because these addresses aren't valid. But as we've done in previous challenges now, we can now use this leaked address to go and find out the correct version of libc to use. So let's go to the libc database here. We've used this in a couple of videos now. Going to clear these, we'll add a new one, and let's go and give it this leaked address. We can't give it a libc base because that's not going to be the correct libc base in this case. We can put in the address here, and in this case then we'll do libc start main ret find. We're going to get a couple of options. I went straight for the option at the bottom, and this will tell us the various offsets then. So it's saying that the offset is this far from the libc base. So if we go and update this and say that our libc base is minus that sorry, not that value there. Yeah, that value there. So we've now got our libc base, and we also want a system function as well. The system is this far off the base, so now that we've got the base, we just add that there, and this should work for us if we try to run this again. Use it against the server. Into interactive mode, we've got no errors. We list, and we can see that we have our flag here, which again I'll not print in this case. You can follow this video and do these steps, and you'll be able to print that yourself. I'm not going to cover it here as well because I've covered it a couple of times, but if you go through the last video released, and some of the others, I can't remember exactly which ones, we downloaded the Lib-C library here and then imported it so that we were able to basically swap between the local and the server versions without having to change all of these offsets. But I'll not do that in this case, and there's no point looking at ROP objects, so there's no buffer overflows or ROP gadgets required, so it's not really needed. And that's been the Nightmare Challenge. That wraps it up for the easy Pwn challenges. Next we'll move on to the hard and extreme, whatever, insane challenges, but I'm not too sure. I might leave it a while before we do those and maybe go back on some reverse engineering or something, but I'll try and get through all of the retired challenges at some point. I'll also be releasing soon just a series on the Veracode Security Labs Community Edition, just because I was preparing for the hacker games that we were doing with the university and figured I might as well try and produce some content at the same time. But yeah, hope you've enjoyed this video. Any questions or comments, leave them down below. Thanks.